All right, everybody, hello, and welcome to our sixth topic, which is variability. So variability is going to cover a couple of topics, specifically variance and standard deviation, which are very important steps on our journey to fully understanding descriptive statistics. We are still doing descriptive statistics here, and describing the data. Specifically, we're going to attempt to describe the spread of data in a meaningful way. So let's start by just talking about what variability is. All right, variability is the amount of spread that scores have around the mean. So we'll be using the mean, a measure of central tendency, to anchor our variability. So variability begs the question, how close or far is any given score in a data set to the mean? Do we have scores that are largely clustered around the mean or scores that are very spread out around the mean? So distributions with the same mean can have very different amounts of spread. So on the right here, I have a few pictures of distributions, all right, data distributions that we've been playing with our describing and displaying data. So here we have three different shapes of distributions, right? We see a skewed distribution, a bimodal distribution, and a normal distribution here, all with the same mean. All right, so if we think about it more, the general shape, all right, when we're trying to describe shape of the data, here we have two different data distributions. One where we have scores clustered around the mean. Right, this example is neighborhoods with housing prices, where there's consistent types of housing, versus maybe a neighborhood with diverse types of housing, right? Maybe one neighborhood has homes that are all very close in price, while others have a lot more spread around the mean or around the center. So the very first part of understanding spread of scores is something called the range, and we've already talked a little bit about the range. We use a range of scores in our hypothesis or our histograms and frequency tables. So here we have the range formally explained. So the range is the difference between the maximum and minimum value of a data set. All right, so we have a range of possible scores. So it takes the two most extreme scores to help explain what scores we could expect for a given data set. So here we have the range. We won't actually be calculating the range in the problems we'll be practicing today, but again, it's our first step to understanding a data set, right, if we're looking at spread. All right, so what we are going to work on calculating today is called variance. We're going to get a formula for variance here in a moment. So variance has a bit of a procedure that goes along with it. Variance specifically tells us how spread scores are around the mean by getting something called deviation scores. So how far does a single score deviate from the mean? We're going to start with an example using this small set of data here. So we'll start by just getting the deviation scores and then summing up the deviation scores. So I'm going to hop over to the whiteboard and I'll go ahead and start us off here. Okay, so we want to get the deviation scores for this data set. So we're going to set this up very much as we would set up, much like how we would set up, say, a frequency table. So I'm going to go ahead and get my values in here. All right, we just have these four values. So what we want to get is a deviation score for each of these values. So I'm going to create another column where we get a deviation score, meaning a score minus the mean of this data. Well, to do this, we first need the mean of the data, right? So the mean hasn't left us yet. So we need to get the mean here, the sum of all the x's over n. In this case, if we add these all up, 8 plus 1 is 9, plus 3 is 12, and then we have an n of 4 here. I'll go ahead and put our n somewhere over here for us to keep track of. Okay, so we have 12 over 4 is our mean, which gives us a mean of 3. Right, mean of 3. So to get a deviation score, we want to know how far each score deviates from this particular mean. So let's go ahead and do that. Let's do what the deviation scores suggest, which is take each individual score and subtract the mean. All right, so what do we get? All right, so 8 minus 3 gives us 5. 1 minus 3 gives us -2, right? A negative number. Nothing to worry about. That's okay. That's just indicating that that particular value is below the mean. All right, so then we have 3 minus 3. That gives us a 0. All right, so let's think about what that means. If we have a deviation score of 0, it means that this particular score, this 3 here, doesn't deviate from the mean at all. And that's true, right? Because the mean is 3. So that should make some sense. And then we have a score of 0. So 0 minus 3 will give us -3. All right, so here's a set of deviation scores. We're determining how far each score deviates from our measure of central tendency. So let's do something else here. As we like to sum scores, right, as we've been doing, we could say sum up these x's, get the sum of the x's is equal to 12. That's, of course, what we plug in right here. But let's get a sum of these deviation scores. Let's go ahead and sum up these values, and let's see what we get. So if we take 5, right, with a -2, a 0, and a -3, our deviation scores come out to 0, the sum of them. That's interesting, isn't it? It's because we've established our own middle point. We've created a center point that we are going to refer to as the center. The mean accounts for every value in its calculation. So we're basically anchoring this data set around the mean. So this is why our measures of central tendency are important, because they help to inform us of further calculations. So let's go ahead and hop back over to the slides, and let's consider what we have here. The question is, what are the deviation scores? We calculated those. Then what are the sum of the deviation scores? It's 0. And we should expect the sum of our deviation scores to always be 0. That means that we're doing something right. All right, so let's go ahead and take a look at this next slide here. This is another one of those slides that contains all of the steps in order to calculate or find variance. And then after that, I'll be showing you the formula for variance, so we will practice this in a moment. So as I always say with these slides, I like to have them here for reference, so if you're taking notes, I wouldn't necessarily write all of this down. I would just take a look here and kind of read through what it is that we're going to try to do. So to actually find the variance, we're going to subtract the mean from each score. We just did that. And then the next thing we'll do is square each of those deviation scores, or multiply it by itself. We'll have a squared deviation score. And then this is a major component to variance. What we're going to do is sum up those squared deviation scores. In fact, we even have a name for this because it's so important to this calculation. We call it the sum of squared deviations, or we shorten it as SS, capital SS. So we will be using that in our calculations here. And then we take our SS and we divide by n minus 1, right, by n minus 1. So we're going to elaborate on this and continue to talk about the formula here. But here it is. Okay, we'll use S squared for sample variance. S squared for sample variance. So S squared is equal to the sum of our deviation scores squared. Right, that's what we call the sum of squared deviation scores, or the SS. And then we have everything over n minus 1. And again, we'll talk more about why we do that -1 in a moment here. But otherwise, we don't have anything too new, all right? So we have a sum symbol, right, capital sigma, telling us to sum up those deviation scores to get the sum of squares. We have all of our x's again. We have scores on a variable x. We have x bar, right, which will be the mean of that particular sample. And then we have n for sample size, the size of our samples here. All right. So let's take a look at just a thought experiment, all right? Let's think about variance, right? Because it's easy to get bogged down in this formula, but let's think a little bit more about what it is. All right, let's consider two data sets here. Let's say these are ages of individuals, right? Maybe I'm surveying ages in my classes. Maybe I take a small subset and I find this among two samples. The first data set here, I have 1, 2, 3, 4, 5 individuals reporting 18 as their age, and 5 reporting 28 as their age. We could get an average here, right? In fact, we would get a mean or an average of something like 23, which is 5 points between each of these. That would be the center here. The average would be 23, even though, right, there's no actual 23 reported in this data set. And we could calculate variance for this as well. We're not going to for this example, but just think about this. Is there some variation in these scores? There certainly is, right? These scores are not all identical. But we can take another data set, which is all 23s, right? Maybe I survey some students and everybody is age 23. The mean would be 23, right? Because all of the scores are equal to 23. But there would be no variance. There is no variance in this second data set because nothing varies, right? Every value is the same. All right, so just something to think about. Before we dive into the calculating, what is it that we're calculating? We're calculating if there is a variability or variance or any type of varying in the scores. So let's go ahead and think a little bit more about the formula. All right, so the formula has a numerator and a denominator. So we're going to take a look at each of those pieces separately here. And then we're going to dive in and calculate the variance for the data that we were just working with. All right, so here's two parts to the formula. So the numerator of the formula is first here. This is the sum of squares. And if we read this, right, if we read the math here, what this is saying is to take the sum of every score minus the mean squared. Right, every score minus the mean squared. And we're going to do this using a table much like we use to calculate percentage. I think tables are helpful in keeping us organized. So I'll show you how we calculate this in the table format. And then we divide by n minus 1. N minus 1 comes with its own name as well. N minus 1 in this case is what we call degrees of freedom. Degrees of freedom. It's a relatively complicated concept that we'll think about very simply for our purposes in the class. So degrees of freedom are the number of scores in a sample that are independent and free to vary. So what does that mean? That means that we have a sample of data, all right? Remember, our statistics are based on samples. And in any given sample, we don't have all of the information available for the population. So if we say go into a calculation like variance and say we have, in this case, we have 4 in our sample, which is very small and not entirely practical. But if we divide, right, our calculation here by just n, we're getting variance that is completely specific to our data set. It means that we're only getting variance that is exactly related to our data set. If we use degrees of freedom and we divide by n minus 1, you can think about it giving the numbers a little bit of wiggle room. What degrees of freedom basically do is say, hey, we know we don't have all of the data, so we're going to leave a little bit of wiggle room for the data, a little bit of margin for error, we might say, to get a variance that might be more accurate for other similar samples. So there's no need to get too hung up on this, right? What we are using it for is just to divide our SS, or our sum of squares, by. We'll talk about degrees of freedom in the future. Degrees of freedom is important for determining cutoff scores for hypothesis tests, which will be a major part of this class in the future. But for now, we just need to know that subtracting 1 from n gives the numbers a little wiggle room and makes it easier to make inferences from our sample to perhaps other samples. Okay, so with that, let's hop back to the whiteboard and let's try out this formula. All right, let's go ahead and give this a shot. Let's say, create another column here. All right, let's actually get here our other color. Let's go ahead and say that we want another column for x minus x bar squared, all right? So our formula is, let me go ahead and get it up here for us. Our formula is that variance is equal to, all right, the sum of our deviation scores all over n minus 1. Okay, so what we're going to do here is we're going to, let me grab another color. We're going to get this here. We're going to get this value for each of our scores. So let's go ahead and start doing that, all right? So what this is saying, our new column is saying, let's square these values, right? Let's square these values that we got, these deviation scores. So if we square 5, we get 25. All right, if we square -2, here's where our rules of math come back into play. If you square a negative number or you multiply a negative number by another negative number, it becomes a positive number. All right, so all of our squared deviation scores should be positive here. 0 squared gives us 0, right? And the -3 squared will give us a positive 9. All right, so let's go ahead and sum these up. Let's sum up our squared deviation scores. So this, all right, this that we're about to sum, this is our SS. If we sum this up, right, we're going to sum all of our squared deviation scores. This is going to become the numerator for our formula, right? So let's go ahead and do that. If we sum all of these up, we get something like 38. Okay, something like 38 for our sum of squared deviation scores. Okay, that's excellent. So if we go back to the formula here, our S squared is equal to that sum of squared deviation scores. So 38 goes up top, and then we're going to put it all over n minus 1. All right, so 4 minus 1. So our S squared is going to give us something like, and again, please do check your math here along the way. Grab your calculator and make sure you get the same thing as me when you do this math for yourself. But this should give us something like 12.67. All right, 12.67. That is our variance for this particular set of scores. So what does it mean? Okay, we get this value, we get this variance value. What does it mean? And in all truthfulness, it doesn't mean too much yet. This is somewhat of a raw score that we're going to use a little bit later to calculate something called standard deviation. So go ahead and hang tight on that. We will get there shortly here. So first and foremost, let's go ahead and hop back over to the slides and let's consider something else. All right, let's consider one more thing. So the sum of squares is crucial to this calculation, right? We need the SS, and then we need to go ahead and divide it by our degrees of freedom to get this variance value. But there is one other way that we can get the sum of squares. All right, we have something called a computational formula for the sum of squares. All right, and here we have it. So SS, or the sum of squares, and I'll mention now as well, S squared is not the same as SS. So we have a lowercase s squared to represent variance, and then we have capital SS to represent the sum of squared deviation scores, which ultimately goes into the variance calculation. So it can be a bit confusing. So we do just need to keep them straight. But here we have a computational formula, all right, for SS. It is equal to the sum of our x values squared minus the sum of our x's squared in a different order because of our parentheses over n. So I know this formula can look a little bit intimidating, but worry not. We're going to calculate this using a table, much like we've been doing. All right, so let's go ahead and hop back over to the whiteboard and let's try out another example. All right, let's try another example here. Let's get a fresh slide. Let's get a fresh data set. So I'm going to put down a fresh data set. I'm going to calculate the variance using the method we just did using the table. All right, so I'm going to put some new data in here. Let's get our x values in here. We will go with a 1, a 9, a 5, an 8, and a 7. All right, so let's go ahead and start by getting the mean. All right, so the mean uses the sum of x. All right, so our mean is equal to the sum of x all over n. All right, so the sum of x, if we go ahead and add this up, we should get a sum here of 30. All right, so 30, and we have 1, 2, 3, 4, 5 values here. So our n is equal to 5. We take 30 over 5. We have a mean of 6. Okay, so thinking to our formula, all right, our standard formula here, the sum of our deviation scores squared all over n minus 1. So the next thing we want to do if we're going with our first method here is subtract the mean from each of these scores here. So let's go ahead and do that. All right. Okay, so we have a difference here of -5. We have a difference here of 3, of -1, of 2, and of 1. So let's try something else here again. Let's go ahead and sum up these deviation scores, and what do we get? Well, we have -5 plus 3 plus -1 plus 2 plus 1. We have 6 in the negative, 6 in the positive, and we're at 0 again, like magic, right? Just like we were in the past data set as well. This is a way to check that you've done this correctly, right? That you've gotten your differences correctly here. Then the next step, if we want to calculate using this method, would be we want to take each of these deviation scores and square them. All right, so remember our negatives go away, so we end up with a positive 25, a 9, a 1, a 4, and a 1. And if we sum this up, right, remember we're summing our squared deviation scores. So this is going to give us SS. And if we go ahead and sum this up, we get 40. All right, and I'll go ahead and label it for us. This is our SS. Okay, this here, this front part or this top part of the formula here, this is SS. It means what it literally states. It's the sum, all right, of the squared deviation scores. All right, so making a little bit of a mess out of our formula, but just trying to drive home here that that's what we're doing. We're summing our squared deviation scores, and then we can plug those sum of squared deviation scores into our formula, all over n minus 1. We end up with a variance here of 10. All right, so this is how we calculate variance in the standard way, but we're going to go ahead and try this new formula as well. And in fact, I'm going to give us a fresh slide here so we can see this through. Let me get our data here. We have a 1, a 9, a 5, an 8, and a 7. All right. We're going to use this formula this time. To get the sum of squares, we're not going to create a table and then sum those squared deviation scores. Instead, we're going to use this more concise, what we call a computational formula. What this really means is some mathematicians played with these numbers enough to realize that we can get the sum of squares this way as well. And I'll show you why you might prefer to use this method. So we have x's here. And now let's think about what we need from this formula. Well, if you look here, all right, we need the sum of x, which is the same sum of x that we used to, say, calculate the mean. So we got that last time. If we add these all up, we have a sum of x is equal to 30. We also need, if we look at the formula, the sum of the x's squared. And this is another important time to consider order of operations, right? If we think about PEMDAS, right, we do parentheses and exponents before we do summing. So we're going to square the x's first in this case, and then sum them. So let's go ahead and square the x's. I've created a column to do so. If we square each of these, we get 1, we get 81, we get 25, we get 64, and we get 49. All right, so let's go ahead and sum these x's squared. If we sum them all up, we get something equal to 220. Okay, and our n is still equal to 5. Okay, n's equal to 5. So let's go ahead and plug in the pieces to this formula. So we have SS is equal to the sum of the x's squared, which we found down here, which is 220, minus the sum of the x's, okay, the sum of the x's in parentheses, and we're going to square that. And we're going to put that all over 5. So let's say that our sum of squares is equal to 220 minus 30 squared will give us 900. Okay, 900 over 5. This gives us SS equal to 220 minus, if we do 900 over 5, we get 180. And then what's our difference here? Our sum of squares ends up equaling maybe something familiar. Let me get another fun color for us here. The sum of squares is equal to 40 here. Okay, is that familiar? Okay, sum of squares equal to 40. If we go back here, using this method, the sum of squares was also equal to 40. So we have two different ways to get to the same end here. All right, we can use this table method in which we're taking each individual score, getting its deviation score and squaring it, or we crunch up the numbers a bit more in this computational sum of squares formula. But they'll both get you to the same place. Because if we think about the formula a little bit more, and let's go ahead and do so, okay? Let's get a new slide. So we have, all right, we have one formula for s squared, which is equal to the sum of x minus x bar squared all over n minus 1. Okay, so this gives us variance. Remember, this is variance, all right? So we can think of this in a more simplified form. We can say, okay, s squared is equal to the sum of square deviation scores. Okay, so this, all right, is the sum of squares. All right, this is equal to the sum of the squared deviation scores. I hope we see the relationship here, right? That this is just somewhat of an abbreviation for the calculation in the variance formula. And we're going to put it over, all right, degrees of freedom, all right, degrees of freedom. So in the very same way, n minus 1 in this case is representing degrees of freedom, okay, or this is n minus 1. So a way that we can sort of think of the formula in a more condensed form. So then SS, right, let's get even another color here. So we have SS here, okay, or we have SS here. And then we have a formula for SS on its own, all right, which is the formula that we just tried out. So all of these are interrelated, all right, these are all related. So if we calculate an SS here, we just got an SS of 40. Let's go ahead and try plugging it into to this formula up here. All right, so we would just do something as simple as, okay, if we go back here, we have an SS of 40 and an n of 5. So we would just want to put, right, s squared equal to 40 over n minus 1. This is going to give us that very same variance that we calculated if we scoot all the way back to the start. All right, so there are lots of relationships here, all right, lots of overlapping of concepts, and we practice this a fair bit. In fact, we have 2 different homework assignments in which we're practicing getting the variance. So to also kind of clarify, we have 3 homework assignments that have to do with this, because I think it's important for us to practice this. So most of it's going to deal with calculating the variance. But if we hop back over to the slides here, all right, we just took a look at our computational formula. As I mentioned earlier, variance is really just a tool for us to get something called standard deviation. Standard deviation is the practical statistic that we use very often, all right? It's often reported in, say, research papers because it is standardized. It's right there in the name itself. And all that we do to get the standard deviation is take the square root of the variance. All right, so we'll go ahead and do that for the 2 examples we just gave. So it's a little bit anticlimactic, right? It's the more important statistic, but all we do is take the square root of the variance. So again, our first homework 4, I believe, is first, or next anyway. Homework 4 has you only calculating the variance, all right? And then we don't calculate the standard deviation until homework 5 or 6. So if you're wanting to maybe come back to this point and worry about this when you work on the next homework, that's okay. But again, it's a very small step in addition to what else we're talking about here. So to get the standard deviation, you find the variance and you take the square root. The standard deviation is always going to be positive, right? Because variance is always going to be positive because it's a sum of squared scores, which will never be negative. So let's take a look here at the formula. It's exactly the same as the variance formula, but we just take the square root. So again, I'll show you how this translates, right? Once you have a variance value, you can just take the square root of it, and that will give you standard deviation. So standard deviation is very important for when we talk about, say, the normal curve, which is a very important topic upcoming in this class. Standard deviation describes the average amount that scores differ from the mean, and how we can place them on a curve and what percentage of data we expect to lie within certain ranges of our scores. So this is back to what we touched on at the beginning. We'll have little variability or a very small standard deviation if scores are close to the mean. And if scores are mostly far from the mean, there's a lot of variability, or we'll have larger standard deviations of our scores. So let's go ahead and hop back to the whiteboard, and I'm going to move us back to, let's journey back to our first example here. So we had a variance value, all right, an s squared equal to 12.67. So we'll use a distinct color here, but standard deviation is reported simply as s, all right? So no s squared, because what we're doing is taking the square root of our variance, right? We see how this kind of works. How we get s without the square is square rooting the s squared. So let's go ahead and do that. To get the standard deviation here, we would take the square root of that variance value of 12.67. We end up with a standard deviation of 3.56. All right, 3.56. So what does that mean? That means that on average in this data set, right, scores varied from the mean about 3.5 scores. All right, so we can take a look at those scores here and think about how that translates. Standard deviation is often used in much larger samples, but of course we are learning and don't want to bog ourselves down, so we're working with smaller data sets. Let's go ahead and try for this one as well. All right, so to get s here, we want to take the square root of our variance value. So if we take the square root of 10, we have a standard deviation of 3.16. All right, and same idea here. This is meant to represent somewhat of an average distance from our scores. All right, so that's it for us for the conceptual overview here of variability. And as I stated, we do a lot of practice with this in the homeworks for this topic. So this is not the last you'll see of this. And make sure to check out the homework reviews if you need more practice with this.